Next, volumetric analysis. Volumetric analysis is an analytical procedure used to determine the amount of substances by measuring volumes. One volumetric analytical procedure is titration. Titration is a technique used to find the concentration of an unknown solution when you know the concentration of another. We add the known solution to a definite volume of the unknown solution until the reaction is complete. By noting the reacting volumes of the two solutions, titration helps you work out the unknown concentration. You can work out the concentration of an acid or alkali using a titration experiment. Because the two will neutralize each other, the reaction will be complete at a neutral pH, which will be noted by color change of an added indicator. In this chapter, we shall see how to perform titration experiments and how to calculate the unknown concentration. The apparatus needed for a titration experiment include a pipette, a burette, a stand with a clamp, and a conical flask. The pipette is used to accurately measure a certain volume of the unknown solution into the conical flask. The burette is used to add the known solution into the unknown. The conical flask rests on the base of the stand and the burette is firmly held by the clamp. A titration experiment basically involves these steps. First, using a pipette, measure a certain volume of the unknown solution and transfer it into the conical flask. Secondly, add a few drops of an indicator. Then, fill the burette with the known solution and record the burette reading as initial reading. Slowly add the solution from the burette to the unknown solution in the conical flask as you swirl the flask to mix the solutions. Stop adding when the reaction is complete. This is the endpoint. The endpoint is marked by a change in color of the solution because of the indicator you added. Record the final reading on the burette, and then subtract the initial reading from the final reading to get the volume of the known solution that has reacted. This volume is called the titer. Repeat the procedure at least 3 times till you get consistent values of the titer. It is important to note that you could have the acid as the known and the alkali as unknown, or the alkali as the known and the acid as the unknown. Once you repeat the experiment and have consistent results, the next step is calculations to find the concentration of the unknown solution. We will perform a titration experiment following these steps, and taking the reacting volumes, we will calculate the unknown concentration. In this titration experiment, we will require the following: 0.1 molar sodium hydroxide, and an unknown concentration of hydrochloric acid, and a phenolphthalein indicator. We will perform a titration experiment to find the concentration of the acid. So using a pipette, we measure 25 cubic centimeters or 25 ml of HCl and transfer that into a conical flask. Notice that the HCl is of unknown concentration. Then we add a few drops of phenolphthalein indicator. The indicator is colorless in acid and pink in base. We swirl the conical flask for the content to mix. Next, we have a solution of 0.1 molar sodium hydroxide. This is the known solution, and we transfer that into the burette up to the 0 mark. And remember, when you are reading the burette, read at the bottom of the meniscus. Now we open the burette tap to allow sodium hydroxide to flow into the conical flask as we swirl to fasten the reaction. You notice that once we swirl, the pink color disappears. The reaction taking place in the conical flask is a neutralization reaction. We have an acid in the flask and a base running from the burette. At end point, the solution will be neutral and the indicator will change its color. Caution and patience is important, particularly in the first experiment, because we don't know when the reaction will be complete. After the first experiment, the subsequent ones are faster, obviously because at least we already have an idea how much volume we need to add from the burette. So keep adding the sodium hydroxide dropwise as you swirl. The white tile gives a better background to see any color changes. The pink color keeps disappearing once we swirl, but at the point it doesn't disappear, we will stop adding the sodium hydroxide. And I guess this is the end point. The pink color has persisted, though I ought to have been more careful than that. But let's work with this. The next thing we need to know is how much sodium hydroxide neutralized the acid. We read the final burette reading. It's 25.4 cubic centimeters. And so 25.4 cubic centimeters of 0.1 molar sodium hydroxide was used to neutralize 25 cubic centimeters of hydrochloric acid of unknown concentration. We need to repeat that experiment 2 more times at least, but let's leave it at that point and find out the concentration of the HCl. Now, during a titration experiment, you record the data in a table like this one. It has room for 3 titration procedures. It has the final and initial burette readings and also the volume used. You record the initial reading before the titration and the final reading once you reach the end point. Volume used is final reading minus the initial reading. The titers should be recorded correct to 1 or 2 decimal places. In 2 decimal places, the last digit should be 0 or 5, and so we don't expect a figure like 25.43 milliliters. The volumes must also be consistent and have an accuracy of plus or minus 0.2 milliliters. Average titer is found by adding all the used volumes and dividing by the number of experiments. In this case, it will be 3. There are usually 3 types of titrations: direct, back, and redox titrations. In direct titrations, a standard solution, that is one with the known concentration, is added to an analyte that with unknown concentration gradually to determine either the concentration, relative atomic mass, or the percentage purity. The experiment we just performed is a direct titration. So we know the concentration of sodium hydroxide but not that of hydrochloric acid. And so we are trying to establish the concentration of hydrochloric acid by reacting it with the sodium hydroxide. This is called standardization. When we find the concentration of the acid, we say we have standardized the acid. In the end, we found the titer as 25.4 milliliters. And so 25 milliliters of unknown concentration of hydrochloric acid was completely neutralized by 25.4 milliliters of 0.1 molar sodium hydroxide. So, what is the concentration of the hydrochloric acid? We go back to our table. Volume of the pipette, the one we put in the conical flask, was 25 milliliters. That is the volume of the acid. In the first experiment, we filled the burette so that the initial reading was 0.0. The final volume was 25.4 milliliters, and therefore the volume used is 25.4 minus 0, which is equal to 25.4 milliliters. This final reading will be the initial reading for the next experiment. Suppose we do a titration and end with a final burette reading of 50.9 milliliters, assuming the burette can hold that. Most will hold up to 50 milliliters. If I have a final reading of 50.9 milliliters, it means that the volume used is 50.9 minus 25.4, which gives us 25.5 milliliters. Let's say I have a burette that can hold up to 60 milliliters. At this point, I will have to refill it up to the 0 mark. So the initial reading is 0. And let's say the final reading for the third titration is 25.3 milliliters. The used volume will be 25.3 milliliters. From here, we calculate the average titer. We have 25.4 plus 25.5 plus 25.3, everything divided by 3, and that gives us 25.4 milliliters. So the average titer here is 25.4 milliliters. Now we have the reacting volumes of the alkali and the acid, and we also know the concentration of the alkali. We can now find the concentration or the molarity of the acid. 25 milliliters of an unknown concentration of hydrochloric acid was completely neutralized by 25.4 milliliters of 0.1 molar sodium hydroxide. Let's find the concentration of the hydrochloric acid. We know the concentration of sodium hydroxide was 0.1 molar. That square bracket means concentration in chemistry. This means that 0.1 moles are in 1,000 milliliters, but we use 25.4 milliliters. How many moles are in there? So we work out as usual. 0.1 moles times 25.4 milliliters over 1,000 milliliters. The milliliters cancel out and we remain with 0.00254 moles. And so 25.4 milliliters of 0.1 molar sodium hydroxide contains 0.00254 moles. This number of moles reacted with a certain number of moles of hydrochloric acid. How do we find the number of moles of the acid that reacted? Remember, when substances react, moles combine in a particular ratio, which we find using a balanced chemical equation. So the equation for the reaction between hydrochloric acid and sodium hydroxide is this one. This is balanced. It tells us that the reaction ratio of sodium hydroxide to hydrochloric acid is 1:1, which means the number of moles of sodium hydroxide that reacts equals to the number of moles of the acid that reacted. So moles of hydrochloric acid is equal to the moles of sodium hydroxide, and it's equal to 0.00254. Does that mean the concentration of the acid is the same as that of the alkali? Not necessarily. Why? Because whereas the number of moles are equal, the reacting volumes are different. As for the hydrochloric acid, 0.00254 moles are in 25 milliliters. To find the molarity of the acid, we find how many moles would be in 1,000 ml of the same solution. We have 0.00254 moles times 1,000 ml over 25 ml. The mls cancel out and we get approximately 0.1 moles. And because these 0.1 moles are in 1,000 ml or 1 liter, this is called molarity. And so the concentration of hydrochloric acid was 0.1 molar. Another example. If 12.5 cubic centimeters of sulfuric acid of unknown concentration completely neutralized 25 cubic centimeters of 1 molar sodium hydroxide, determine the concentration of the acid. Again, we have two reacting volumes and a concentration of one of the reactants. We find the concentration of the other. In other words, we standardize the sulfuric acid. We know the concentration of sodium hydroxide and the reacting volume, so we use that to find the number of moles of sodium hydroxide that reacted. Concentration of sodium hydroxide is 1 molar, and this means 1 mole is in 1,000 cubic centimeters, but only 25 cubic centimeters reacted. So how many moles are in there? We have 1 mole times 25 cubic centimeters over 1,000 cubic centimeters. Cubic centimeters cancel out and we remain with 0.025 moles. So 25 cubic centimeters of 1 molar sodium hydroxide contains 0.025 moles. These moles reacted with some moles of sulfuric acid. How many? We can know that if we get the reaction ratio. From where? From a balanced chemical equation. This is the equation. You notice that the ratio of sodium hydroxide to sulfuric acid is 2:1. And so if 0.025 moles of sodium hydroxide reacted, then those of sulfuric acid that reacted will be half of those. That is a half times 0.025. Giving us 0.0125 moles. As for the acid, the 0.0125 moles are contained in 12.5 cubic centimeters. So what is the molarity of the acid? It is the number of moles in 1,000 cubic centimeters. So we say 0.0125 moles are in 12.5 cubic centimeters. How about 1,000 cubic centimeters? We work out 0.0125 moles times 1,000 cubic centimeters over 12.5 cubic centimeters. Cubic centimeters cancel out and we remain with 0.1 moles. And again, because it is contained in 1,000 cubic centimeters or 1 liter, this is also the molarity. And so the concentration of sulfuric acid is 0.1 molar. Next, we look at how we use titration to find the relative atomic mass or formula mass. Again, by knowing the reacting volumes or masses and the concentration of one of the reacting species, we can find the relative atomic mass, particularly of solids. Let's take an example. 0.5 grams of A carbonate completely reacted with 20 milliliters of 0.5 molar hydrochloric acid. Calculate the relative atomic mass of A, and you are given the relative atomic mass of carbon is 12 and that of oxygen is 16. The first thing to always remember is that substances react in ratios of moles. So first we find the number of moles that we can. In this case, we can find the number of moles of the acid that reacted. We know the concentration of hydrochloric acid is 0.5 molar, and that means 0.5 moles are in 1,000 mLs. How about 20 milliliters? We have 0.5 moles times 20 milliliters over 1,000 milliliters. The milliliters cancel out, and we remain with 0.01 moles. What is the mole ratio? We get a balanced chemical equation. Take note of the chemical formula of a carbonate. Considering that a carbonate is a divalent radical, it means that A is also a divalent metal. This is important in writing the chemical equation. So we have that chemical equation. Mole ratio of a carbonate to hydrochloric acid is 1 to 2. Number of moles of a carbonate is equal to a half the number of moles of hydrochloric acid, and that is equal to a half times 0.01, giving us 0.005 moles. Now we find the formula mass of a carbonate. We know the mass, it's 0.5 grams. We also know that number of moles is equal to the mass over the relative atomic mass, or formula mass. And so formula mass is equal to mass over the number of moles. And so we have 0.5 grams over 0.005 moles. That gives us 100 grams per mole. Now, the formula mass of a compound is the sum of the relative atomic mass of individual elements. And so for a carbonate, A plus 12, the relative atomic mass of carbon, plus 16 times 3, the relative atomic masses of 3 oxygen, is equal to 100 grams per mole. And so A plus 60 is equal to 100, and A is 40 grams per mole. Next, finding percentage purity. Now, when we find the percentage purity, we are simply finding the fraction of the substance that is the active ingredient. For instance, in drugs, there is the active ingredient and the carrier material, which is inactive. The same goes for fertilizers. To find the percentage purity, we react the substance with another of known concentration. We note the reacting volume of the known, find the number of moles that reacted for both substances, and using the relative atomic mass or the relative formula mass of the unknown, we convert moles into mass, and then we work out the percentage. For example, 2.15 grams of a sample of sodium carbonate obtained from the Solvay process reacted completely with 40 milliliters of 0.5 molar sulfuric acid. Calculate the percentage purity of the carbonate. This means that not all the 2.15 grams of sodium carbonate was active. We find how many grams was active. So we first find the number of moles that reacted. We know the concentration and volume of the sulfuric acid that reacted, so we can find how many moles of that acid reacted. Concentration of sulfuric acid was 0.5 molar. That means 0.5 moles are in 1,000 mLs. How about 40 milliliters? We have 0.5 moles times 40 milliliters over 1,000 milliliters. Milliliters cancel out and we get 0.02 moles. So how many moles of sodium carbonate reacted? We get the mole ratio from the chemical equation. There is the balanced chemical equation. And so the mole ratio of sodium carbonate to sulfuric acid is 1:1. So the moles of sodium carbonate are equal to the number of moles of sulfuric acid, and that is 0.02 moles. The relative formula mass of sodium carbonate will be given by 23 times 2 plus 12 plus 16 times 3. That gives us 106 grams per mole. Mass is equal to number of moles times the relative formula mass. That is 0.02 times 106. That gives us 2.12 grams. So 2.12 grams is the active mass, but we had a total mass of 2.15. So the percentage purity will be given by 2.12 over 2.15 times 100. That gives us 98.6%. The next type of titration is back titration. A back titration is a titration method where the concentration of an analyte is determined by reacting it with the known concentration of excess reagent. You can think of a back titration as a normal titration done in reverse. It is also called an indirect titration. Basically, we use a back titration when we need to determine the strength or concentration of an analyte and we have a known molar concentration of an excess reactant. It involves two steps. 1. An analyte is reacted with excess reagent. And then, a titration is conducted on the mixture to ascertain how much of the excess reagent remained in step 1. This way, we can know how much reacted in step 1 and hence find the concentration and the relative formula mass of the analyte. Let's take an example. 15 milliliters of potassium hydroxide is put in a conical flask. 35 milliliters of 0.5 molar hydrochloric acid in excess is added and the mixture is stirred. The resulting solution is then completely neutralized by 10 milliliters of 1 molar sodium hydroxide in a subsequent titration procedure. Calculate 1. The number of moles of the acid that reacted with sodium hydroxide. 2. The number of moles of the acid that reacted with potassium hydroxide. And 3. The molarity of potassium hydroxide. Now, in this experiment, excess hydrochloric acid is first reacted with potassium hydroxide. It means some acid reacted and some remained unreacted. This unreacted acid was then neutralized by sodium hydroxide in the titration procedure. So we need to first find the total number of moles of hydrochloric acid in 35 milliliters of 0.5 molar hydrochloric acid. We know the molar concentration of the acid. It's 0.5 molar. But we had 35 milliliters. So how many moles are in that volume? 0.5 moles are in 1,000 milliliters. How about 35 milliliters? We have 0.5 times 35 over 1,000, and that gives us 0.0175 moles. And so the total number of moles of hydrochloric acid in 35 milliliters of the solution is 0.0175. Next, we find the number of moles of sodium hydroxide that reacted with the acid. That is the acid that remained after the addition to potassium hydroxide. The concentration of sodium hydroxide is 1 molar, and that means 1 mole in 1,000 mLs. But only 10 milliliters neutralized the excess acid. So how many moles are in the 10 milliliters of sodium hydroxide? We have 1 mole times 10 milliliters over 1,000, which gives us 0.01 moles. Next, we find the number of moles of the acid that reacted with this sodium hydroxide. We get the mole ratio from the chemical equation. There is the chemical equation, and the mole ratio of sodium hydroxide to hydrochloric acid is 1:1. Therefore, the number of moles of hydrochloric acid that reacted with sodium hydroxide in the titration is 0.01 moles. And so in total, there were 0.0175 moles of hydrochloric acid. Out of these, 0.01 moles reacted with sodium hydroxide. So how many moles had reacted with potassium hydroxide? We simply subtract. 0.0175 minus 0.01 will give us 0.0075 moles. And so 0.0075 moles of hydrochloric acid reacted with potassium hydroxide. From here, we can get the number of moles of potassium hydroxide that reacted from the first experiment. We get the mole ratio from the equation. There it is, and the ratio is 1:1. So the moles of potassium hydroxide is equal to the moles of hydrochloric acid. That is 0.0075. This number of moles are contained in 15 milliliters of potassium hydroxide. So what is the concentration or molarity? We find the number of moles in 1,000 ml of such a solution. So 0.0075 moles are in 15 milliliters. What about 1,000 milliliters? That will be 0.0075 times 1,000 milliliters over 15 milliliters, giving us 0.5 moles. And because these moles are in 1,000 milliliters, this is the molarity, 0.5 molar. Another example, X grams of calcium carbonate is put in a conical flask and 30 milliliters of 0.5 molar hydrochloric acid added. The excess acid is then neutralized by 5 milliliters of 1 molar sodium hydroxide in a subsequent titration. Calculate the value of X. In other words, we find the mass of the calcium carbonate. We can get the relative formula mass of calcium carbonate. If we get the number of moles that reacted, we will then get the mass. The acid was in excess, so first we find the total number of moles of hydrochloric acid in 30 milliliters of 0.5 molar hydrochloric acid. So 0.5 molar means that 0.5 moles are in 1,000 milliliters. How about 30 milliliters of the same solution? How many moles will be in there? We have 0.5 moles times 30 milliliters over 1,000 milliliters. The milliliters cancel out and we remain with 0.015 moles. Next, we find the number of moles that reacted with sodium hydroxide. These are the number of moles that remained after reaction with calcium carbonate. We can find that by knowing how many moles of sodium hydroxide reacted. We know the concentration of sodium hydroxide is 1 molar, and we also know that 5 milliliters of that had been used. So 1 mole is in 1,000 ml. How about 5 ml? We get 1 times 5 ml over 1,000 ml, giving us 0.005 moles. Now we find the number of moles of hydrochloric acid that reacted with sodium hydroxide. We get the mole ratio from the chemical equation. There it is. That is the chemical equation. The mole ratio is 1:1, and therefore the moles of hydrochloric acid is also 0.005. So the total number of moles in 30 milliliters of hydrochloric acid was 0.015. 0.005 moles reacted with sodium hydroxide. So how many had reacted with calcium carbonate? we simply subtract. 0.015 minus 0.005 will give us 0.01 moles. Next, how many moles of calcium carbonate reacted? We get that from the mole ratio. We write the chemical equation. From this, the mole ratio of calcium carbonate to hydrochloric acid is 1 to 2, and therefore the moles of carbonate is equal to half the moles of the acid, that is a half times 0.01, giving us 0.005 moles. Now we know the number of moles of calcium carbonate that reacted. We can find the mass. Recall that number of moles is equal to mass over the relative formula mass. The relative formula mass of calcium carbonate is equal to 40, the relative atomic mass for calcium, plus 12 for carbon, plus 16 times 3, the relative atomic mass of 3 oxygen, giving us 100 grams per mole. Mass will be equal to the number of moles times the relative formula mass, and that is 0.005 times 100, giving us 5 grams. And so 5 grams of calcium carbonate is what had reacted with hydrochloric acid. The third type of titration, which is less common, is redox titration. Redox means reduction oxidation. Both processes occur simultaneously. In redox titrations, indicators are not required because the changes in oxidation states ultimately results in color change. For instance, potassium manganate 7. Manganate 7 ions are purple in color. They are reduced to manganate 2 ions, which are colorless. Dichromate ions are orange in color, and they are reduced to chromium ions, which are green in color. Redox titrations are done in the exact same manner as the other titrations, except that indicators are not used. Molar gas volume. Molar gas volume is the volume that 1 mole of any gas occupies. The molar gas volume is the same for all gases. This volume changes when measured at different temperatures and pressures. We know that a gas expands when heated, so 1 mole of a gas would occupy a larger volume. If a gas is in a sealed container and is put under a higher pressure than the atmosphere, then it occupies a smaller volume. It has been found that 1 mole of any gas occupies approximately 22.4 liters under standard temperature and pressure. Standard temperature and pressure is 0 degrees Celsius and 0.986 atmospheres. It has also been found that 1 mole of any gas occupies 24 liters at room temperature and pressure, which is 20 degrees Celsius and 1 atmospheres respectively. Combining volumes of gases. Now, consider a reaction between hydrogen and oxygen gases to form steam. From this equation, we see that 2 moles of hydrogen gas react with 1 mole of oxygen gas to give 2 moles of steam. So the mole ratio of hydrogen to oxygen to steam is 2 to 1 to 2. Interestingly, this mole ratio can be extrapolated to volumes. This will mean that 2 volumes of hydrogen react with 1 volume of oxygen to give 2 volumes of steam. Putting in figures, it could mean that 20 cubic centimeters of hydrogen react with 10 cubic centimeters of oxygen to give 20 cubic centimeters of steam. This observation is summarized in Gay-Lussac's law of combining volumes, which states that when gases react, they do so in simple whole number ratios to one another and to the product if it's gaseous, provided all the volumes are measured under the same conditions of pressure and temperature. In the same thinking, nitrogen and hydrogen form ammonia according to this equation. This equation is balanced. It means that 1 mole of nitrogen reacts with 3 moles of hydrogen to produce 2 moles of ammonia. Extrapolated into volumes, it means that 1 volume of nitrogen combines with 3 volumes of hydrogen to yield 2 volumes of ammonia. If we put figures, it would mean that 5 milliliters of nitrogen gas will combine with 15 milliliters of hydrogen gas to yield 10 milliliters of ammonia gas. However, you need to be careful when one of the reactants is in excess. For instance, consider the Haber process for ammonia synthesis from nitrogen and hydrogen. Imagine on a certain day we produce 4,000 moles of ammonia with an excess of hydrogen gas. Whenever you see a reactant being described as in excess, that means there is more of it in the reaction than is necessary. So it is not this chemical that will determine the volume of the product formed, and you should focus on the other reactant, nitrogen in this case. This is called the limiting reagent. So how much nitrogen did we use? First, balance the equation. For every 2 moles of ammonia, we need 1 mole of nitrogen and 3 moles of hydrogen. You can also think of it like this. 1 mole of ammonia need a half mole of nitrogen and 3/2 moles of hydrogen gas. How much nitrogen did we use to make 4,000 moles of ammonia? We simply divide 4,000 by the mole ratio, which is 2, and the answer is 2,000 moles. Let's take a few examples. First one, 10.6 grams of sodium carbonate is heated and decomposes according to this equation. What volume of carbon dioxide is liberated at standard temperature and pressure? We find the number of moles of sodium carbonate that reacted. That is given by mass over the relative formula mass, which is 10.6 divided by 106. That gives us 0.1 moles. From the equation, we can get the mole ratio of sodium carbonate to carbon dioxide. That is equal to 1:1. And so the moles of carbon dioxide produced is also 0.1. How much volume is that? We know that 1 mole of a gas occupies 22.4 decimeter cubed at standard temperature and pressure. And here we have 0.1 moles. How many decimeter cubed are those? We have 0.1 moles over 1 mole times 22.4 decimeter cubed. That is equal to 2.24 decimeter cube, which is also equal to 2.24 liters, which is also equal to 2,240 cubic centimeters. Another example. At standard temperature and pressure, 0.28 grams of a gas occupies 224 cubic centimeters. What is the relative molecular mass of the gas? We find the number of moles of the gas. We know that 1 mole of a gas at STP occupies 22,400 cubic centimeters. And here we have a gas occupying 224 cubic centimeters. How many moles are those? We have 1 mole times 224 over 22,400. That gives us 0.01 moles. Relative molecular mass is given by mass over the number of moles. That is 0.28 over 0.01, which gives us 28 grams per mole. Last example. 75 cubic centimeters of nitrogen gas was reacted with 165 cubic centimeters of hydrogen gas. Assuming the reaction went into completion and that all volumes were measured at the same temperature and pressure, calculate the volume of ammonia formed and the total volume of the gaseous mixture at the end of the reaction. This is a case of a limiting reagent. First, we write the equation. Nitrogen plus hydrogen gives ammonia. The mole ratio of nitrogen to hydrogen to ammonia is 1 to 3 to 2. The volume ratio will also be 1 to 3 to 2. Between nitrogen and hydrogen, 1 is the limiting reagent. But which one? We put in the volumes. Assuming all the 75 cubic centimeters of nitrogen reacted, we would need 3 times that volume for hydrogen. That is 75 times 3, which is 225 cubic centimeters. But then, we only have 165 cubic centimeters of hydrogen, and so hydrogen is the limiting reagent. If all the 165 cubic centimeters of hydrogen reacted, we will require a third of that volume for nitrogen. That is a third of 165, which is 55 cubic centimeters. So the reacting volumes will be 55 cubic centimeters nitrogen and 165 cubic centimeters hydrogen. According to Gay-Lussac's law, the volume of ammonia will be twice the volume of nitrogen. That is 55 times 2, giving us 110 cubic centimeters. The total gaseous volume at the end of the reaction is equal to the volume of the ammonia formed plus the volume of the unreacted nitrogen. That is 110 cubic centimeters of ammonia plus we had a total of 75 cubic centimeters of nitrogen but 55 reacted. The difference is 20. If we add that, we get 130 cubic centimeters.